Hello, my name is James White. Welcome to the Critical Tech Podcast. I'm the CEO and co-founder of Carbon Critical, and I'm joined today by my Chief Operating Officer, Michael Paszti, and our distinguished guest, Weikang Li, who is the co-founder and Chief Technology Officer of ExPost Technologies. Today we'll be talking about the risks associated with disposal of lithium-ion batteries and new technologies that ExPost is developing along with Carbon Critical to mitigate this risk as it appears in the battery waste stream. Our host is Joe Maniotis, and he will be moderating our discussion. Over to you, Joe.
Great, and it's nice to have everybody here, and it's nice to have you make that introduction, James. So let's get right into it. First of all, Carbon Critical is partnering with ExPost on this technology, and we'll talk a little bit about that later. What I wanted to start with is how, obviously, these batteries are a major concern because of the sheer amount of them. Now, the statistics are that it's estimated that over 11 million metric tons of lithium-ion batteries will be thrown away by the year 2030. And these batteries are causing more explosions and more fires every year. Okay, so since we're using them more, a recent report in 2023 showed that there were over 50 reported fires at waste and recycling facilities across the US alone. It's clear that as these batteries are reaching the end of their life and we're seeing more and more of them, we're facing some serious challenges in how to handle them safely. So I want to go into more depth about what's happening. Weikang, let's start with you. First, why are these fires happening more frequently in recycling centers?
Sure. Of course, we have more batteries in waste stream, and if you really consider the mechanism behind why lithium-ion battery can catch fire, it is because you may consider lithium-ion batteries are energy conveyor. So it has energy inside. So once you contact the positive side with negative side, of course, we call it short. And once it's short, a lot of electrons will flow, and it will heat up the whole thing. And worst case is that inside the lithium-ion batteries, we already have an oxidizer, we already have reducer. So once it touch with each other, it causes more oxidative reductive reaction. It's a chemical reaction that will release a lot of heat. And besides that, we also have flammable organic components inside the batteries, which we call it electrolyte. And these flammable electrolyte can easily be ignited and then cause more fire. So overall, it's more like a chain reaction that leads to a bigger fire when the lithium batteries start to catch fire. So that's the mechanism behind.
And this happens also when when they're dead, they're discharged. These fires can still happen.
Yes, even it's discharged. If we will not talk about a fully discharged batteries, it can still catch fire. The answer is unfortunately yes.
Mike and James, I just want to talk a little bit about what the processes are, or what is actually allowing for. I mean, if a battery gets sent to a recycling facility, how is it catching fire? What's behind it? What's happening? Can you tell me a little bit more about that?
I can feel that one from my personal experience in lead acid battery recycling and other recycling areas. There's a mechanical process at the beginning of all these recycling facilities where something comes in, it gets broken into pieces, usually it's sorted and further processed. So when you subject a lithium ion battery to that breaking process, so for example, in the lead acid battery recycling process, the first step is literally called the breaker, and it just crushes lead acid batteries into nothing. If you throw a lithium ion battery in there, you'll end up with an explosion, a fire, surely, and quite possibly damage that takes a lot of money and a lot of time to fix, and even injuries to people. So imagine that same kind of situation in, say, a paper recycling facility. Obviously, that's going to create a huge conflagration. Any recycling facility with plastics and everything, you're gonna see an equally large fire there. And you can just look up the news reports and see that these are not trivial fires at all. They are in some cases just catastrophic. That things that make headlines, and they cause disruptions in that recycling business for months or even years.
Explain that a little bit to me, James. What are the disruptions? How long does this go for? What happens to the factory and so on?
Well, based on research that we've seen, the principal effect is a rise in insurance rates for transfer stations and waste handling facilities that handle these types of waste streams. And whereas fires were relatively well controlled and relatively uncommon and easy to suppress in the past, typically, um, they are now much more common. The fires can be much more catastrophic. They're much more difficult to extinguish because of the nature of a lithium battery fire and the fact that fire departments and fire suppression systems are not necessarily equipped right now to handle these types of fires, which are driven by a runaway chemical reaction. So I think the principal way that this manifests itself is through greatly increased insurance costs. In our research that was provided to us actually by Weikang, we found that insurance rates that had been on the order of $50,000 per year were in some cases over $1 million, and other facilities that did not have effective means to mitigate fire risks could not get insurance at all. So they were self-insured
Wow.
at this point, while still facing an elevated risk of a catastrophic loss. So the problem is real, and it manifests itself in the form of either the non-availability of insurance or greatly increased insurance premiums. So it can be expressed in dollar terms for these facilities.
All right. So talk to me about some of the technology that ExPost and Carbon Critical are working on.
So because we understand the nature of lithium-ion batteries, especially the mechanism why it catch fire, so we identified removing electrolyte and that will neutralize the whole system. So we're actually working on a project developing new method to completely extract the electrolyte from the cell. We're not only talking about the solvent, but we're also talking about the salt associated with the lithium-ion batteries. So the reason behind are very straightforward. So in terms of the hazardous level of lithium-ion batteries, we are actually talking about two different types of hazardous waste. One we call the electrochemical hazardous. Another one is a chemical hazardous. So when we talk about the lithium-ion batteries catching fire, we're actually talking about the first one, which is electrochemical hazardous. And people typically ignore the chemical hazardous risk associated with lithium batteries. So in our project, we are developing new extraction method and to completely remove the electrochemical hazardous as well as the chemical hazardous. So that's the project me and James are working on.
And can you tell us a little bit about some of those processes to remove the chemical hazards?
Yeah, so of course, sure, we start to identify the lithium-ion batteries for sure, and then we still go through a safety shredding process. This shredding is associated with an inert environment, as well as a very, I would say it's a environment to control the atmosphere inside the shredding unit. So we drastically prevent any potential fire hazards or explosion that can happen during the shredding. And the next phase is actually, we call it extraction, which is we are using special chemicals to extract the solvent and the salt of the electrolyte out of the shreds. So the shreds is a lithium-ion battery shreds. And of course, once we shred the batteries, all the inside components will be exposed. And then that's where we get a chance to completely extract the solvent and the salt from the shred. And by separating the electrolyte from the cathode, anode, or other components of the batteries, we drastically mitigate the fire potential or explosion opportunity of the batteries. So that's what we're doing.
All right. So how does the technology that Carbon Critical brings fit into this process? James, Mike?
So Carbon Critical is a domain expert in the use of supercritical carbon dioxide for industrial processes. And this fits or aligns perfectly with our core expertise in that field. We found that supercritical fluids, supercritical CO2 in particular, is a highly effective solvent to remove electrolyte. And also, it is, of course, an inert gas, so there is no fire risk when working in that CO2 atmosphere. And it's an effective heat transfer media. So it actually can perform three roles in this instance, and can do them without releasing any toxic compounds to the external environment. The working fluid is completely recyclable, so no fluids are ever lost, and there's minimal need to replenish fluids in the process, and there's no waste stream associated with the working fluid. So in that sense, the supercritical fluid, once you've made the capital investment to generate and contain these supercritical fluids, the fluid itself is infinitely recyclable. The cost is almost nothing, and it is highly effective in the sense that it performs these three functions simultaneously.
What are the biggest technical challenges associated with a project like this? Like, I know that there's a lot of partners in and there's a lot of parts to the process. Can you give me some sort of idea on what are the technical challenges and how those parts are fitting together, and how you foresee everything working? Because I think the main thing that I want to sort of get to is how to make this a larger process. Like, in the end of the discussion, I'd really love to sort of bring that back to how this fits into the recycling plants, processes, and so on. So can you speak a little bit on that?
Uh, sure. So if we talk about technical challenges, definitely there are different layers of technical challenges for sure, including how we really design the system, how the system can operate. But all these can fall into a main topic, which is the cost to operate or the cost to manufacture this type of system. So we are trying our best to control the overall cost, not only into manufacturing it, but also to operate it, because I think this is very critical even to recycling facilities, to other battery recycling companies who are really using, who will use this system in the future. So then it boils down to the chemicals we're using, also how we design the shredding system, how we design the extraction system, how we combine them together. So there are different layers of challenges behind. And in terms of the meaning of design this unit, we actually are proposing even more than what we are doing with project, because we know currently consumer electronic batteries are still small, so we can still handle that batteries. Let's say we just store the batteries inside our cabinet or storage room. That's not a problem. But since we know that we are moving forward to electrification world, meaning we're seeing more and more EVs on the road. Then when we talk about the batteries from electrical vehicles, that's the really big headache. Nobody would be able to store those big battery pack inside the backyard. That's definitely not a choice. Then how we handle those batteries during transportation, then we think our system, if we can successfully demonstrate that in consumer electronic waste stream, we also have a great potential to demonstrate this project in handling EV batteries. That's the way how we think about this project. So it's a good starting point, and we will tap into a bigger and bigger batteries, and of course eventually push it to more commercialization. That's what we're doing.
So just to follow on to what Weikang said, another maybe underappreciated facet of the battery recycling economics is that there are substantial costs to compliance with DOT regulations for shipping waste lithium-ion batteries, and the transportation costs for those items sometimes can equal or exceed the scrap value of the batteries themselves. It's particularly acute with LFP batteries, which essentially have no scrap value right now in the United States. So by performing this neutralization step and reducing the battery to shreds at the point of collection, we are greatly improving the economics of transporting these batteries to some centralized location where they can be recycled. And that should not be underestimated either, because one of the reasons for the low recycling rate for lithium-ion batteries is that it is simply not economical to aggregate all these tiny little batteries into one place, transport them at great expense. By the time you've done that, there's no profit left over for the actual recycler. So it's sort of a truism in many ways that if a process is not economically viable, it will never scale. But we do need to solve the problem of millions of tons of waste batteries somehow. So by improving the economics of this process, I think we're going to be able to fundamentally impact the rate of recycling for batteries.
And so I just wanted to touch on that a little bit. Maybe Mike, you could address this from a process point of view. How would it work and how would it become economical?
I'll expand on what James said, and currently, and I've had experience with this personally, transporting live batteries, in other words, intact whole batteries that still have electrolyte and are in various states of charge, is a very, very costly thing. Even batteries with high recovery value, lots of nickel, lots of cobalt, to transport these, you need a special carrier. You can't, in terms of density, they're on a flatbed truck effectively, which is not a very efficient way to transport anything. And the way you have an efficient recycling program, recycling anything for that matter, is to have scale. Okay, so these are going to be large scale recycling facilities, and they're going to be bringing in materials from various distances, quite far distances in fact, but only if you can reduce this to an inert pile of dirt essentially. Then your trucking becomes very efficient. Then you don't need special carriers. Then you have no fire risk. You don't need placarded carriers, and there's no flammable liquids. So that it all makes it possible to create a recycling system across the continent, really, and around the world that looks actually quite familiar to some of the recycling systems we have now for other types of commodities, uh, whether it be plastic, paper, cardboard. You've got these things called MRFs, material recycling facility or material recovery facility, depending who you ask. Um, these are where the fires are happening today. So you'd have something like that for the lithium ion batteries, probably closer to urban centers where most of the batteries will be coming from. But before you send anything there, you have to inertize all these batteries. And that's where our technologies come together to create that inert material. It becomes a tradable commodity now. Now it's inert, and I can ship it. I can pack it up into a container ship it somewhere to the highest bidder, or I can send it to the MRF or the recycling facility in my state, province, region, whatever. So, it's a familiar recycling paradigm that we're trying to create. It's not you know rocket science. The trick and the value we're creating with this project that we're working on is that you're allowing that transportation ease to happen that never existed before. And you're at the same time, because you're making recycling easier and more cost effective, you're removing hopefully batteries from falling into other streams and getting discarded improperly. I mean, there is no bin for recycled batteries or any kind of batteries, and it's a very um, difficult thing to do right now. Recycle even EV batteries. You're picking up the phone, calling people, trying to find where to send this thing. But it is becoming easier, and with our technology, it becomes easier still and safer and more cost effective.
All right, so Weikang, you've built this big consortium. to do this project. And tell us a little bit about the partners and also the funding that you received from the Department of Energy, which was a huge grant and something that obviously tell us about the impact that had on ExPost and the technology that you've developed, and yeah, and about the partnerships you formed.
Sure. Yeah. Let me start from why DOE is funding this direction. So according to DOE's projection, based on many data analysis, definitely in the US we need the EV batteries, and the cobalt is one of the essential element to make the cathode active materials, which will be used in battery manufacturing. So where US can get more cobalt, that's always a question. So currently, almost 90% or even more cobalt is from DRC, under developed country in the South in Africa, and there are a lot of issues associated with the cobalt mining there. And a good news in the US is that a lot of people just have consumer electronic, and you can easily find the lithium cobalt oxide batteries inside your consumer electronics. And according to the projection, if everyone just push the consumer electronic into the recycling stream, then the US will have enough cobalt even till 2030, 2040. There's no lacking cobalt issue. So DOE said, okay, what's the obstacles? Why people are not returning the consumer electronics? Why they are not willing to do that? Of course, under the same portfolio, we have projects funded by DOE trying to encourage people to return those consumer electronic batteries. We also have projects, let's say, our project, how to how to make the transportation of batteries or battery recycling more economic, how to make it more efficient and cost effective. We even have more projects in the downstream, how to analyze if there is enough cobalt and how we extract the cobalt from the battery shreds or from the black mass created during the recycling process. So overall, it's all about the element. It's about a resource. They really want to secure enough cobalt resource inside the U.S. And of course, in other world, DOE wants to the general public to join the recycling effort. So it's good for the environment. It's also good for the whole country. So that's why in the whole scenario, we're getting funding to work on this specific topic. And as for the consortium we're forming, so we do have different companies. We have a non-profit organization. We have universities. We have national labs. Specifically, I want to mention that we are honored to work with UL Research Institution, which has extensive experience on battery safety and battery recycling topics. So they are providing more insights into this project, how we can handle the batteries with a safety manner. And also we are working with Argonne National Lab, so they are helping us analyzing the residues from our process to see if the residue can fulfill in a safe transportation. And also we are working with 3 universities, including University of Chicago, University of California, San Diego, and the University of Tennessee. So all these universities are helping us to shape the project in a proper way. For example, we're talking about VOC control, we're talking about waste control, but first of all, we really need to understand what we are dealing with and what we are producing through this whole process. And a lot of categorizations will be performed to understand the materials inside this project. And of course, we also are very happy to work with Carbon Critical. Their expertise on extraction will definitely help a lot, and also their expertise on machine designing will help us really make this project a very successful one. So that's the background and how we formed the consortium.
I was reading about a very similar problem that the United States faces to the problem of cobalts just disappearing in the form of waste batteries, and nobody knows where it goes. And there's another very similar analogous problem, which is the penny. And it turns out that the US Mint, because pennies are used in circulation, but nobody people receive pennies in change, but nobody ever uses pennies to pay because it's too inconvenient. It's not worth the effort of counting out your pennies or saving them, or you don't want to walk around with them in your pocket or in your wallet. Um, so pennies are given out all the time, but because there's no real incentive to use them as currency, because they're worth so little and they're so bulky, they're continually disappearing. They go into jars, they go into drawers, people just throw them in the trash. Um, and I think, when I was listening to Weikang speak, it just struck me, ooh, this is just like the penny. It's this thing which we have to have, it's part of our currency, but to the recipient of the penny, it has no value at all. Once you've received it, you've gotten your change, so the transaction's complete, and functionally, pennies just disappear all the time, and so you constantly need to make new ones. And um, it's a good analogy, but I wouldn't say there's like a ready solution to the penny problem. The proposal is to just not have pennies. Uh, in the sense of lithium cobalt oxide batteries, we actually want to get those. And it also gives rise to the idea of a deposit or a fee that is paid at retail to fund collection and recycling efforts. That's not yet in place in the United States, but it's one of the policy solutions that is also being looked to increase the rate of recycling and to improve the domestic supply of materials in the United States. I think the other interesting point, which is sometimes lost or maybe not brought to the forefront in a lot of these discussions, is that, unlike, say, a gallon of gasoline, once you burn the gasoline, it's in the form of carbon dioxide, it's in the atmosphere, you can never get it back in any meaningful way. The lithium and the cobalt and the electrons and everything else that's used in a lithium-ion battery energy storage system, every one of those elements is recoverable and recyclable infinitely. And so it's a really important distinction as we move from the hydrocarbon age to the lithium age. The lithium that is the electrochemical energy transfer mechanism is infinitely recyclable. It never goes away. And so the incentive to create a functional and cost-effective circular recycling system is tremendously high. It is foreseeable that at some point we might never mine another gram of lithium or nickel or cobalt. We would have everything we need to power our economy indefinitely, just based on a effective circularity. And so, this is the first days, the first years in which this is being thought of, and it's being done at some scale, but maybe it's not perfectly economical just yet. But who knows what the world will be in 30 or 50 years? It could be a very, very different world, and we're sort of laying the foundations for what will come in the future.
I just want to extend on that. You're right. It's going to be a different world, but actually it's going to look a lot similar too, because the lead acid battery you buy at the store right now, that lead was mined in the 70s, or like more than likely, the vast majority of it. So they've got more lead in circulation being recycled than there is actual mining. So this is not entirely new. We can do it. We can do it for lithium-ion batteries. Totally doable. And by extension, sodium-ion batteries, magnesium-ion batteries, all the whole shebang, all those battery materials. So they can go around and around forever. I just wanted to add also, you talked about sort of policy mechanisms where maybe there's a deposit fee, maybe there's some kind of recycling incentive fee that enables this recycling process to work. Again, that's being done already in other areas. You've got these kind of eco fees, tucked into the cost of all sorts of things, everything from spray cans for aerosols to electronics you buy at Best Buy. I mean, there's little fees in there that fund these collection mechanisms that collect AA batteries, for example. It varies by state, of course, and by country, but these things exist. So we're really building on, I would say, proven models in other areas. This is very doable. And there's just a massive future ahead of us. I mean, if you thought recycling e-waste was big, recycling EV batteries is orders of magnitude bigger.
In terms of lithium-ion battery recycling, as Mike mentioned, it's definitely doable, and we definitely need to do that. The obstacles why it's a relatively low recycling rate is because of the technology. So we really need to work on new technologies to improve the recycling efficiency, lower the cost, and of course they will also facilitate it to a higher recycling rate. And that's what ExPost and as well as Carbon Critical, we are working on this area. We're working in this area. Yeah.
All right, so Weikang, I want to hear a little bit about your journey and how you got to where you are. I like to ask that of everyone that comes on the podcast. Tell us a little bit about yourself.
So yeah, so I actually graduated as a PhD in 2019, and then after that I immediately joined UC San Diego as a postdoctoral researcher. So a well-known professor named Shirley Meng was my PI at that time. So I was extensively working on different cathode active materials for lithium-ion batteries in terms of how to synthesize those materials, how to modify those materials so that they can perform better in batteries, what's the degradation mechanisms, why it degrades in terms of batteries or materials. And then I was introduced to a very interesting project associated with recycling topic. So the whole project was focusing on how to scale up a ground level lab-based technology to a kilogram level for as a pilot or a small pilot demonstration. So I kind of figure out a better mechanism how to scale up this process, and then it raised really a big interest in myself to further scale it up. And that's where we have a idea. We need to form a startup company to commercialize this great idea. And this is actually associated with a technology fall into a direct recycling area where we don't actually decompose or completely destroy the materials from the lithium-ion batteries, but rather we keep the component, we rejuvenate them, and we directly use the rejuvenated materials in new battery manufacturing. This is also associated with the project that we discussed just right now, the shock project, because let's say considering the electrolyte as a component inside the lithium-ion batteries, we're not burning them, we're not just to dump them into the ocean. We're actually extracting the electrolyte, and of course we hope we can reuse the electrolyte as it is, or we can just do some easy purification process. Then the extracted electrolyte can be used in the next round of battery manufacturing. So all these are associated with each other, and it's both, and it pushing to a concept called a direct recycling. So we consider this as a true recycling rather than mining and the refining.
It's amazing stuff, and it's been great having you on the podcast. Weikang, thank you very much. James, Mike, always a pleasure.